talking about is mixture of materials and manufacturing at the same time. Probably all of you noted for last 10 years or so, or less than 10 years, additive manufacturing became an important area of interest for worldwide. And in a way, I'm talking about past, present, and future. This is popular now, but it's a very old technology. If you look at the slide, in 2012, Economist magazine came up with this cover that the third industrial revolution. Now, it's third industrial revolution, but if you look at the original patent, the first patent on three-dimensional object preparation with stereolithographic technique by Chuck Hull, it was issued on 1986. Patent expired already. Beeman's patent on selective laser sintering, that was issued on 1990. That's also expired. Then my patent on metallic additive manufacturing, that was issued on 2000, that also expired. Now suddenly it became third industrial revolution when all the patents have original patent has been expired. So I don't know how many of you have seen the movie Back to the Future. So I essentially say that this is the community is going back to the future. And to add more, 2800 BC, almost 5,000 years back, Egyptian has made pyramid using step-by-step manufacturing. So additive manufacturing, the concept, has been around for 5,000 years. Now suddenly it's become too hot. In fact, those of you who are familiar with Factory 4.0, that also features very prominently additive manufacturing as the method for the future. So, but its past history is almost 5,000 years old. And already, these are some of the things, research from my own lab. Aerospace industry already adapted this for repairing blisk. Oil and gas industry is used for surface wear resistance. Defense have the picture you see, the right-hand corner is basically torque converter for tank, and basically restoration of those tank component was adapted already by defense. Medical industry used for making what you call hip replacement. Another is the GE90 engine is made out of carbon fiber, but in order to avoid any breakage from bird impact, they use a titanium shield for that, and that is also made by additive manufacturing. Right hand side, the last corner picture where you see is with essentially putting integrated valve seat for auto industry, and I introduced that to Nissan in 1990. So it's a very old technology, but suddenly it became very popular. So what's present you can do? There are already 8 different systems in the market. Now, there is a stereolithography where you're using laser light to photosynthesize polymer. 3D systems came up with a long time back. That's available in the market. 3D systems also bought from Texas, University of Texas, Austin, this technology to make laser sintering. Then you have got fused deposition by Stratasys, where you're using, instead of a laser, you're using a heater to melt the polymer fiber and lay it down like a toothpaste. And that's very cheap and very popular now. Then polyjet processing for like using inkjet printer, putting the material, that's in the market. 3D printing is Z Corporation. They put sort of a glue on powder and make a shape. Robocasting is essentially using robot to do the small deposition. And then laser net shaping by Optomec. That's also using powder, and the laser is essentially variation of laser cladding. You can put different kind of powder at the same spot. and create an alloy. In fact, recently people are using this technique to explore the whole phase diagram. For high entropy alloys, you are using 4 or 5 different elements at the same time, and creating a phase diagram for that was difficult and time consuming. Now, using this technique, people are trying to study the whole phase diagram, putting different composition at the same time by varying the powder flow. And last but not the least, Arcam, which is now part of General Electric, they're using electron beam to melt the powder and create a shape. So all different, 8 different things are commercially available, and now the new techniques are coming almost every other day. And to sort of in a light-hearted way, people are even printing food. Left-hand side is basically digital shortbread created by additive manufacturing. People are using for design complicated heels for the ladies' shoes. On the other hand, the right-hand corner, you are basically saying sort of a 3D print of a food. You can make printing all kinds of human organs and parts. And that's possible because you can have polymer which can keep the genes alive, and you can print that using many of those typical 3D printing systems. So technology is growing time and bound. Now, one of the problem of or challenge of additive manufacturing is software. You can say you are building things by pixel, but if you're making pixel by pixel, what kind of software you use to essentially make 3D shapes? And in fact, originally, almost 20 years back, we got involved with Tata Consulting Services in India to come up with a software based on Unigraphics, where you can make all kind of complicated shape. You see, this is the shape offered by a group of 20 industries worldwide, that if you want to have a confirmed 3D printing process, you have to show that you can generate concave surfaces, you can step surfaces, hollow surfaces, elliptical, all kind of different surfaces. So we gave that. The TCS come up with a software where this slice layer by layer, and all kind of complicated shape can be used using this kind of software. So one of the thing which an Indian company pioneered, now there are tens of commercial software available, everybody is copying. And I'll show you the more things which is happening in India itself as I go along. Another advantage of this additive manufacturing, by putting material pixel by pixel and creating a 3D shape, since you have that capability of putting different material at different pixel, you can use a topological design. Using a topological design, you can make a component where you need different properties and the different part of that component. You can put different material. In fact, an Indian company called Bharat Forge in Pune, they're looking into this kind of technology to make the die for forging applications. And when I was visiting them a few years back, when I asked them how they're competing with China because labor is so cheap, and with a smile, the CEO, who is a MIT graduate, took me to a place and showed me that instead of competing in the labor cost, they're developing a technology where the software properties in India can be used to come up with this topologically designed dies and put different material in different places to make it design more robust, so that they can come up with a new component design much faster than other countries. And that's how they keep up the competition. And now Bharat Forge is #1 forging company in the whole world. So there are bright spots where people are using their brain cells to come up with a new technology. Now, as an example, I'm giving that you can design all kinds of different material using this technology. Negative city is another challenge for engineering. So using topological design, you can see the blue is the chromium and green is the nickel. You can make a design where the material, when it got heated, will shrink rather than expand. And this was the next picture is where we made the part and we put a dime 1 centimeter wide coin to show that this is about 2 inch square. You can make all, design the material with the property you want instead of what Mother Nature gives you. So that gives you enormous power. At the same time, these are the die, seat belt, D-ring die. Tool steel is put on copper, and being a metallurgist, you know that copper and steel is like water and oil doesn't mix. But due to the rapid solidification, you can extend the solid solubility and can come up with a die. The tool steel will give you the long life, and copper will give you a very quick heat extraction. And most of the die, 75% of the time is spent on thermal management. So copper reduces that time by almost 30%. At the same time, you can also design using a topological design a sort of a scaffold for your bone. And once the scaffold is done, you can make it very light, at the same time very stiff. And once the scaffold is done, you can harvest the genes from your bone marrow, put it in the scaffold, and within 6 weeks, the extreme right-hand corner picture is showing you the bones are being formed from your own genes. So think of the situation where you have formed from your own genes. You don't have to, is biocompatible. You don't have to take all this anti-rejection drug all the time. So that helps you sort of in human health quite a lot. So these are different applications already being sort of done. And this shows that, this negativity, this paper was published some time back. This negativity material, when you put it under the test, you can see it's always shrinking rather than expanding. So you can do all kind. You can also generate nanocrystalline and nickel aluminum powder phases and things like that. So what I'm trying to tell you is that additive manufacturing is basically a technique where material scientists can use that to create nanostructure or topologically designed structure to get the right type of mechanical or physical property. So it's a tool which you can use from developing a new alloy to a new structure. Another thing, and which we already have patent for this, it's not patent pending anymore. You can directly write a single crystal. Those of you know the high efficiency jets use a single crystal blade to avoid creep. And this is the picture we are showing that we took the N5, one of the most difficult nickel superalloy patented by GE. And in cooperation with GE, we wrote a single crystal, not only just simple wall, all kinds of different shape, so that instead of using a tungsten mold, you can just use the software to create the turbine blade. So again, to show you the capability which this technology provides you. Another example of what's going on now, we designed a machine for design and built and supplied machine for Army Tank Command. One of the problem, like your aircraft carrier, 20% of the weight is to carry just a spare part, and spare parts are generally pipes and tubes, which is mostly air. Whereas we have a patent, the patent number is in the top. By using this remote manufacturing technique, you can send your digital data. Additive manufacturing is basically digital process. If you have a fabricating machine inside your ship, you can basically come up with any kind of shape you want and produce the part. So you can make any part anywhere, any size for any material. So that gives you another capability. And one of the problem, Tank Command being a defense organization, they're extremely worried about stealing of the data from the ether. So you can encrypt the data 264-bit is very difficult to break. And using a data compression technique, you can compress the data by 95%. And one of the BE College connection for that data compression idea came from Professor Pal Chaudhary of Shibpur. So he retired now, but that's also, so what I'm trying to point out that the BE College has been involved in many different technology for a long time, and it's a question of just looking for it. So that's another area of advancement using this additive manufacturing. Using mathematical modeling technique, you can essentially plan, find out what is the composition distribution and liquid velocity distribution, and that's basically transport phenomena modeling. So this particular model use heat transfer, fluid flow, and mass transfer at the same time to get an idea how the liquids are flowing. And the fluid flow is important because as a metallurgist, we don't care whether how the fluid flow, but as an engineer, you have to remember that flow creates the surface shape, because surface is not uniform because if you go to a seashore, you see the waves are always breaking into the shore. Same thing happens is a small melt pool. So you get all kinds of funny shape on the surface that you can control by controlling the fluid flow. At the same time, fluid flow is also responsible for homogenization and mixing of different alloy. So that gives you a theoretical capability to predict the microstructure. But the question is, predict but how do I measure it? Because it takes days for me to take the sample, cut into small pieces, make the foils, go to the TEM and SEM and see what the composition property. So one of the challenges, can I predict the microstructure during the process and rectify that? So my rest of the work on the future will just focus on that. But in the mathematical model, another problem of the model is the complicated multiphysics model takes several days in a supercomputer to converge. On the other hand, typical time for interaction for metal and the laser is 2 to 10 milliseconds. So we have to develop a geometric form type solution so that that information can be used online. So that's one of the challenge still available for people to work on it, those who are interested in mathematical modeling. And another example I like to give, a few years back, I was invited to Pune Engineering College, and what I saw, the undergraduate club designed a 3D printing machine using FDM technology, that means fused deposition method, where they're melting plastic and make a complicated shape like Ganesh, and that costs less than 40,000 rupees, which is $600. So undergraduate kids in India can make a machine which can compete to rest of the world for making any kind of complicated shape. And Ganesh, it's not a simple shape. They have done that. So I hope students in BE College will get, or IIEST will get involved doing that. Now the future, those are things which is being done in the past, was being done now. Future is smart additive manufacturing. The idea is certify as you build. And that means you have to develop a technique where you can do in situ phase and defect detection. Because unless you do that, you cannot correct your mistake, and product you make is wasted. Now in a standard manufacturing, mass scale manufacturing, the thing you do statistical quality control. And if you're making a 1 million part, you can take every 1,000 part, break it and check it and see whether it's good or bad. That Detroit does that for car industry. They loses about $500 million a year for those kind of quality checking. So you can avoid that and forget about Detroit. Overall, US industry loses something like $60 billion a year for quality issues and checking things like that. So there is a big thrust worldwide to see whether I can find out the quality during the process and take the corrective action to avoid those waste. And as I mentioned, Detroit itself loses about $500 million a year. So this is a thrust which I started focusing on a few years back. And one of the solutions we come up with is especially laser-based processes or arc-based processes. The many manufacturing process create plasma during the manufacturing. So one of the idea we came up with is if I look at the light, and light is very enlightening. Light contains all kind of information, the phase information, the composition information, if there is any defect. So what we have done, we developed a technique and patented that. By looking at the light itself, we developed an algorithm looking at the different spectra from the plasma. By looking at developed an algorithm which, by looking at those spectra, can tell you whether there is a defect like holes, or there's a porosity, or lack of penetration, or what type of microstructure. So we call that smart optical monitoring system, and it's already installed in Olding Institute in PSG in India, in Coimbatore. The idea is very simple. If you look at the sort of a light coming from the plasma, you attenuate them, use the mirror, and then use basically a diffraction grating to break down the light into different wavelengths, and you can get a sort of a resolution of 0.5 nanometer. So you can break down all kinds of different material, and that every element, when it gets ionized, it causes a signature emission. So by doing that, we can identify, and the intensity of those emission tells me how much of it. And that has got sort of creating a lot of interest. And that's the system we developed. And when Ford licensed it, university came to me and say, hey, why you are giving it to Ford? Why don't you make it yourself? And I said, I'm a poor professor. Where can I get the money to start a company? And so university went to the state, gave me startup funding to start this company. So that's the system looks like. It's basically 9-inch long, 6-inch wide, and 3-inch deep. And this blue fiber, it collects the light from the workstation and it does all the analysis and gives the information. And is already installed in USA, China, India, Korea, Australia. It's every day the countries are increasing. So what we do, when you look at the plasma, by looking at the nature of the emission, we can find out whether there is a defect or not, especially porosity. There's a small holes created if the deposition is not correctly done. And we have patented that. And this particular technology is becoming very attractive to industry because then they can find out the defect online instead of waiting for weeks of TM and SEM and all those kind of things. So that's sort of creating a lot of interest. What we find, to our own surprise, that even if the defect is subsurface, we can pick that one up too. And so what you see is this, the software we developed is whenever there is an anomaly in the plasma, we can put this red line during the defect, and so not only the surface defect, we can also predict what are the subsurface defects in the material. And this is just to give you an example. This is the process you're depositing, and you can see online, you're seeing all the spectra, and we can analyze that. And in fact, I just filed a patent last week. We can even determine the virus like COVID-19 and other proteins using the similar technique, if I can ionize those. So this sort of a kind of technique is giving us what material we are depositing, what is the composition, what kind of defect, things like that. Now, it's a very good idea to have those information, but to give you an idea how expensive is this defect if you don't certify that online, cost of design change for a turbine blade is about $10 million. Cost of certification of a new blade is about $50 million. And total engine certification costs GE about $1 billion. So if we can identify the defect online, that will really save a lot of money for major high-tech industries. And one of the problem is additive manufacturing is for low value. If you compare to number of turbine blades made and number of cars made, is very small volume. So we cannot really use a statistical quality control because it won't be valid for a small sample. You need a bigger sample. So online concurrent quality control is imperative. So we start looking at it more carefully, and we found that using the spectral technique is very useful and quick. And in the collecting light, you can do acoustic emission, you can put thermocouple, you can all kinds of other ways of looking at the process. But question is that they are very slow. Light moves at the rate of 186,000 miles a second. So you can get the data very quickly, and electronics is your bottleneck. So you can find out those information looking at the light. And what I will talk about in the next few thing is using direct writing of single crystal and in situ diagnostic using the light. I'll use that example to show that what kind of information I can get just looking at the light. Now, how to write a single crystal? And those of you, I'm talking to the metallurgists, so I assume you know how the single crystal is made. And the critical point of making a single crystal is your temperature gradient at the solid liquid interface has to be maintained carefully and within a very small narrow range. Okay, that's the challenge. And this type of work was funded by National Institute of Standard Technology, NIST, in the USA. And what we found that if I combine laser, induction heating, and cooling plate at the bottom, by controlling it carefully, I can maintain that temperature gradient at the interface very carefully. And once we do that, we tried with all kinds of different alloys, Praxair, different alloys, different alloys, and we found that yes, I can control effectively for almost any alloy. And you can. There's another trick which I haven't told you. That is, if I'm going to make a single crystal, I have to start with a single crystal. You need the seed. So what we found, if I don't start with a single crystal, when you deposit, if you look at the EBSD, I'm getting all kinds of different grains going in a different direction. Whereas if I start with a single crystal, you see, EBSD tells you I'm also maintaining, if I maintain the temperature gradient carefully, I'm also growing single crystal. So that gives you, and you already got a patent on this, that gives you a sort of a solid technique to grow single crystal without any mold and things like that. That paper was published in Metrans a few years back. If you search under my name, you'll find that. So you can directly write a single crystal. And this I showed you before. But what you can do to ensure is a single crystal doesn't have any defect. So things you try to look at, what are the chemical identification, whether I know the composition, what % ratio of the element, defect detection, differentiate between single crystal and non-single crystal, and preferred angle of dendrite. All those you can find out from the information in the plasma. And we basically developed a regression model for composition based on the line intensity ratio. And using this equation, we can essentially estimate what is the composition of the material we are putting. Another technique we did to make sure whether you're in a single crystal or polycrystal, we deposit basically material One plate is base plate is single crystal, another is polycrystal. And you can see the material deposited in a polycrystal. Same process parameter, everything. Non-single crystal is giving you polycrystalline growth, whereas single crystal base giving you single crystal deposition. So by using this kind of technique, we try to identify and differentiate the spectra deposited in a different base plate, and by comparing that, we can find out whether I'm growing a single crystal or polycrystal. And we can also sort of differentiate by looking at the plasma. We can also differentiate basically, was the tilting of the plate, what kind of edge acceleration. And so by doing the EBSD before and after melting, we can also find out what kind of texture you're growing, what direction single crystal is growing. So all kinds of information is all hidden in the light. And if you take the electron temperature versus intensity ratio of different material, you'll find it slightly changes layer by layer. So essentially, by doing the calculating this, estimating the ratios of this, we can also find out what is the micro hardness. So not only we are looking at the composition, the defect, now I am getting into mechanical property. And this detail of this, I'm not going to in detail. The detail of this, what we found out, if you especially take the ratio of magnesium 2 and magnesium 1 line for aluminum alloys containing magnesium, by this intensity ratio started giving me mechanical property. So as a metallurgist, our golden rule is to find out what is the relationship between the processing parameter, microstructure, and mechanical property. So what we revealed in the last 5 years of work that show that by looking at the plasma during the process, I can tell you the defect, I can tell you what is the mechanical property, and I can also sort of from there we can find out what is the yield stress versus Vickers hardness. So if I know the hardness, I can also find out yield stress of the material. So all these all coming into sort of putting that into a nice ribbon and give you the information. We can also found that collecting the light and looking at the ratio, we can give you the crystal orientation too. So what you are seeing here is I'm trying to make you metallurgists unemployed, because most of those things you can find out from the process itself, so you don't have to run to the microscope all the time. And what we found is just quick way to show that there's a sort of when there is a spectrum of strong periodicity, we can sort of also get, when you are depositing in a circular fashion, we can find the relations which direction crystal will grow. For composition and phase identification, what we have done, we collected the light, deposited with alloys without phase transformation like chromium iron or nickel iron. They are soluble after a large extent. And also with phase transformation like titanium iron, nickel aluminum, nickel titanium, depositing that, collecting the light, and developing our algorithm for signal processing, we can tell you the composition too. But for that, we have to develop a calibration curve, different element, what are the composition versus the ratios. And you can see, not only get the composition, we found using a theoretical, using a growth of curve theory, as sooner the line intensity ratio, the slope changes, the phase changes too. So not only we can get the composition, we can start identify the microstructure, all from plasma. Okay, so this has now we have a very strong collaboration with the chairman of the material science department in our university. We are applying. We have basically working with national labs and all kinds of other national institutions. How we can use these online diagnostics to design new alloy, make new alloy, and get most of the information online, and then validate that using an TM and SEM after the process is done, so that we are getting 100% confidence in optical measurement online rather than post-mortem. This is another example of nickel aluminium, and each time you see the slope changes, the structure changes. Now, question is, one of the question when we start presenting that in TMS, the Materials Conference, some of my colleagues was asking, "Oh, the plasma is always fluctuating. How do I know? I'm getting the right signal." What we wanted to show that if you take the ratio, then it's pretty much stable. Okay, so what you're doing, you're basically take the line intensity ratio versus time, and give you an example like chromium. It has emission at both 424.88 nanometer and 426.84 nanometer. So the ratio is stable. So using that, essentially, we found that line intensity ratio is independent of intensity fluctuation. So by taking the ratio, we can sum out the process fluctuation you see, you can avoid that. The last but not the least, trying to stay within the time, we use that information. Then the advantage of being a metallurgist in a mechanical engineering department, that I have also colleagues who works all kinds of controls and other things. And what we found that I take in that information, feedback into the 3D printing system, and by doing that, I can remove the defect before the production is complete. Now, this is the real-time temporal characterization. We got it, and then with the feedback loop, when you run it, most of the defect is gone. We already got the patent on this, and another relevant story related to India, the PSG Institute in Coimbatore already licensed it, and they are in the process of making a machine based on this patent, which will be exhibited in IMTEX International Exhibition in Bangalore in July 2021. So a lot of the technology I'm developing, already Indian organizations have started licensing and adapting that too. Now, another quick relationship that is cyber-enabled integrated digital manufacturing. So US Navy is really interested that how you can come up with a manufacturing environment where somebody gives me the sort of a drawing, and I can take that information, develop a control algorithm, use some of the information from the model, and then put that into the machine, so that whole process is pretty much controlled by knowledge and create the part I want. So that's sort of one of the major area of the whole closed loop circuit for this is our major emphasis now. Now, question is, I'm in the academia. My academic hat, I have to create students with PhD. So one of the questions I'm trying to solve, which is not funded because generally industry or agencies are not interested in that. I am basically taking the plasma, which is guided by quantum mechanics. At the same time, using that plasma information, I am predicting microstructure, which is guided by continuum mechanics. So what's the relationship? And if you believe Einstein, his view was quantum and continuum mechanics, thou shalt not meet. So that's one of the things, and I'm scratching my head and keeping me up in the night to see whether I can come up with this correlation, because I have an experimental proof that I can do that. Now I have to develop the theoretical connection to do that, to see that it's what's the reason behind it. So with that, my summary is we can do the in situ identification of the phase transformation, in situ identification of the defect, in situ identification of the composition, in situ identification of the crystallinity. So it's possible to certify as you build. You can reduce the wastage and quality issues, and possibility of replacing some of the expensive and time-consuming post-mortem material analysis like SEM, X-ray, etc. So with that, thank you for your attention, and I'll take your question.